So, okay, let me start again. So yeah, I'm Peter. The work I'm presenting I did as a PhD student, supervised by James and Duncan, and I'll also be showing some collaborative work that I did with radii that was on comparing to a different method that I'll get to later, and then with Dan Harris and Chase Cabot, who were doing experiments to compare with this work, and they're at Brown University in the US. So what we're thinking about are liquid droplets, and liquid droplets appear in a lot of different settings sort of around us. So in clouds, you've got drops of rain flying around that were to collide with each other to eventually fall as the raindrops that we see. In inkjet printers, you've got drops of ink splashing and hitting a surface. In combustion engines, you've got drops of fuel flying around and then hitting each other. And then if we want to cool down a hot surface, a very classic way of doing that is by spraying it with water, which then evaporates. And there's a question that links all of these is the question of, well, when do these drops bounce apart, or rather, when do these drops merge together? So to focus on one of these problems in particular, just want to think about the sort of length scales of the things involved in one of these processes. So here we've got a sort of big scale storm, which can be, say, hundreds of kilometers at its sort of largest scale. And then if I want to have a weather forecast, I'd sort of hope that I could have accuracy to, say, maybe 1 kilometer nearby me. In a cloud itself, we've got these droplets of water that are flying around, and that one of these larger drops is going to fall as rain and gather up its surrounding ones. And these drops are generally sort of sub-millimetric size, hundreds of microns in size. But then when we look at one of these in particular collisions, we've got a trapped layer of the air that's between these two drops, and these air layers, as we can see later, can be sort of hundreds of nanometers thick. And so if we compare the size of the sort of cloud that we first started thinking about, the whole storm system, down to the air between these drops, we've got, say, 1 trillion orders of magnitude, which is a pretty extraordinary range of sizes that we're actually talking about. The process that I'm really going to be talking about today, though, is this final problem of when two individual drops are impacting with this air between them. So I want to really focus on two examples that I've looked at during my PhD. So the first is the collision of two head-on droplets. We've got two drops that are coming on, colliding. A thin layer of the gas is trapped between them. This gas gets squeezed, but in the case that I'm showing here from these experiments, it's enough that the drops will then bounce apart. And this work has been published by me and my supervisors, and it was this paper that I was awarded the Lighthill-Thwaites Prize for. But I also then want to talk about a problem that I've looked at more recently, which is of a drop hitting a bath of liquid. So now we've got a drop that's falling, it pushes down on the bath, but again, a very thin layer of the surrounding gas is trapped, and that's enough in this case to allow the drop to bounce. Okay, so taking a brief digression, here is a related problem to these drop impacts. This is of a drop hitting a solid surface and splashing, which I think when we think about drop impacts is what we're often thinking about. And in particular, when we think about sort of often fluid dynamics approach this by saying, okay, the surrounding gas is sort of not really important. The gas has got a tiny density, it's got a tiny viscosity, and then hopefully we think, okay, we can ignore the gas, just focus on what the liquid is doing. But what this experiment showed that if you can have a drop that will happily splash at atmospheric pressure, but if you if you decrease the surrounding pressure of the gas, surrounding pressure of gas, that's enough to completely suppress the splashing of the drop. So that all that has changed between these two experiments is the pressure of the air that this experiment is being done in. And so suddenly, the properties of the gas can matter a huge amount. And although I'm not looking at splashing, I'm looking at bouncing drops, we're going to see the same thing where the behavior of the gas and the pressure can make a huge difference to the outcome of these collisions. So here's the prototypical problem that I've been looking at for the drop-drop case. So this is a slow speed impact. We've got two drops that come in, they squeeze together, a bit of the gas gets trapped, but then this gas layer bursts and the two drops merge together into a larger drop. If I increase the impact speed here, this goes through what we've been calling the soft transition, where now more gas gets trapped, the drops to form more, and this gas layer is now strong enough to allow the drops to bounce apart. If I increase the impact speed even more again, then the dynamics of this problem go through what we call the hard transition, where now the gas gets squeezed and eventually the gas layer gets punctured, and again the drops will merge into a larger drop. So we've got a very non-monotonic transition here. If we go increase the impact speed at low speeds, the drops merge, and then they bounce, and then they merge again, which I think is surprising and perhaps not what we would have thought would happen. And it's only this intermediate range of speeds at which drops are able to bounce. So let's talk a bit about what I was actually doing, which is wanting to use computational and mathematical modeling to understand how these collisions happen. So drop collisions have been simulated and modeled on a very wide range of scales using sort of what I think of as a sort of hierarchy of models. So on the one extreme, you can do full 3D simulations where you resolve fully the gas and the drop. And in 3D, as this example here shows, these are incredibly expensive simulations to run, sort of thousands and thousands of CPU hours to just resolve even a small part of this. But these are able to resolve these very sort of violent splashing dynamics. We can take a step down on this hierarchy and assume what we call axisymmetry. So this takes us from a sort of full 3D simulation to one where we sort of assume that the collision is head-on. So in this case, it's a drop hitting a solid that's coming straight down. And we can sort of assume that there's a symmetry, but that if we look at it from any angle, we have the same thing. And that reduces our 3D problem to a 2D problem in cylindrical coordinates. But here's an example of a simulation from a paper a couple of years ago where they were assuming axisymmetry, but still fully resolving the gas and the drop in full. On the other extreme, people have used sort of potential flow problems to sort of look at this mostly analytically, where they assume a very simple expression for the flow profile inside the drop and then expand it in terms of some polynomials and can analyze this also sort of almost analytically. But in assuming something like this, you can only assume that the impacts are very soft and there's actually very little deformation of the drops. Where what we've done fit in is sort of in between. So it's at this lower end of the sort of computational cost end, what we're doing, where we'll be fully solving for the flow inside of the drop, but we're using lubrication theory to resolve the gas flow. I'm going to explain all of this as the talk goes on, but I want to just make the point that what I'm doing is in a sort of very broad hierarchy of different simulation strategies for this drops, and that sort of this fits in at where we've made various assumptions to make this less expensive, but we're still able to fully resolve what's going on in the drop. So, as I say, here's my drop. I'm assuming that we've got a drop that's impacting sort of a plane of symmetry here. So this dashed line is representing a second drop that I've implemented purely through symmetry. So this is my head-on collision of two drops. I've just drawn it vertically instead of horizontally. So these drops are colliding at some speed. And I'm going to solve computationally the Navier-Stokes equations for the flow inside of this drop. So we're fully resolving the fluid dynamics of what's going on inside the liquid in the drop. Then what we want to do is we want to have a model for what's going on in this trapped gas film. So, okay, first of all, I've then got a free surface of my drop where I'm going to solve for, where we've also got surface tension, which we call in the blast stress, but this is basically surface tension that's applying on this surface. And then we've got some stress due to the trapped gas film. And it's this gas stress that we want to try and have a simplified model for. So the thing we want to observe is that this gas film is very thin compared with the radial extent of the drop. So for sort of standard drop sizes of sort of roughly millimeter size drops or a bit smaller, these gas films can be sort of 1,000, 10,000 times thinner than the size of the drop. So what we want to do is we want to use something called lubrication theory, which if you study fluid dynamics, you might have seen before, but I want to quickly give an overview because I think this is where some of the sort of mathematical part of this modeling really comes into it. So here I've got two free surfaces, which I'm calling y is h over 2, so y is minus h over 2, so I've got symmetry. This thing is the thickness of h, and it varies across the x extent of my film. And I'm going to say I have a characteristic length scale in the horizontal direction that's some capital L, then I have a characteristic height scale H, and then I'm going to assume that this ratio epsilon is small, so that this is sort of my small parameter that I then want to exploit. So here is the horizontal component of the Navier-Stokes equation for this drop. So if you've not studied much fluid dynamics before, this is just Newton's second law. So this is the acceleration. So the u here is the velocity. Time derivative of the velocity gives me the acceleration, and then these are the forces. And I've got a force given by a pressure gradient and the force due to the viscosity in the gas. Now, what we want to do is we're going to think about that my y, that I have a very sort of, when I compare my x length, my y scale to my x scale, that this is very small. And so the incompressibility tells me that my velocity scale in the vertical direction also needs to scale like epsilon. So if we now look at our components, let's start over here. So I have my time derivative of my velocity with derivative with respect to time. So if my u scales like u and my time derivative is going to scale like the velocity, the length scale divided by the velocity will give me a time scale. And so this is sort of order of magnitude how my time derivative will scale. And I can do the same thing to all my different components in my equation, where here my y coordinates, this is my vertical coordinates, I'm assuming scales like epsilon. So it's like epsilon times by this length scale. And if I look at all the components in my equation, I can see that this term, this du second derivative u with respect to y, scales like 1 over epsilon squared, so that when epsilon is small, this term here is much, much bigger than all the other terms in my equation. Except I've also got this pressure scale. So I'm also going to assume that this pressure scale, sorry, let me rephrase that. I have a choice, so I can choose whatever scale for my pressure I like. And I'm going to choose a pressure scale that's going to balance the largest term in this equation. So if I choose my pressure scale to look like this, then this pressure term will balance with this large term in my viscosity, and then all of that I'll be left with once I assume that the other terms are small is this equation here. If I repeat the same thing for my vertical component of the Navier-Stokes equation, I do the same process, put in my scale for the pressure that I worked out from the other equation, and I can actually see that now this pressure term is overwhelmingly much, much larger than all of the other terms in the equation, and that all that I'll be left with from my Navier-Stokes equation in this sort of thin, again, remembering I'm assuming that this thickness is much thinner than the horizontal extent, all that I'm left with is this. So if I've got my two surfaces are moving at some velocity, I can integrate this equation to get this. This gives me, so I know what the profile of u is across my thickness. Integrated again, so now this gives my volume flux across the thickness. So I've got an exact description in terms of my pressure derivative and my thickness of how fast the fluid is flowing. And then from conservation of mass, I know that my equation looks like this. Okay, I realize this has gotten quite complicated. Doesn't matter if you couldn't follow it. The main point is that by assuming that I've got this thin length ratio, assuming that my gas film is much longer than it is thick, I can write down a single equation that describes the evolution of my pressure. So if I come back to my picture of my drop impact, I've got my drops impacting, I'm solving Navier-Stokes in the drop, and then I'm solving this single differential equation that we've just had a go at deriving for my gas flow inside this film. And the same process also gives me the stress due to the gas. Okay, so take stock here. I've now got a complete description of a system of equations for this drop impact. So we can take this system of equations and put it in our favorite differential equation solver or fluid dynamics simulator. And what you will find is that these drops will always bounce. So no matter how fast you make your initial velocity, this gas film, it will always be strong enough, the pressure will always be large enough that the drops will just bounce apart. And so it turns out what's missing is a force that will act when these two drop surfaces get very, very close together. There's actually a force that will pull them together. And what this is driven by the van der Waals interaction between two liquid surfaces. So between my two drop surfaces here, where there's very thin, there is this disjoining pressure that will pull them together. And the strength of this can be measured in experiments or by doing chemical calculations, and you can get a strength in terms of this A parameter. And this force goes like this A over h cubed. So this only becomes large when h is very, very small. And with this, you will now find that if you make the impact speed large enough, that the drops will now merge at some speed. But you get the wrong speed. So if I solve this system of equations, I will find that this model says that I have to make, for a particular case, I have to make the drops move at this speed to make them merge rather than bounce, but in the experiment suggests that it takes only half that critical speed. So there is something still missing from our model here in order to predict this critical speed accurately. And so what's wrong is that although we've said that our gas film is thin, it turns out that our gas film is actually really, really, really thin. So here's one of those components of my lubrication equation. This is the component that's driven by this pressure gradient. And our films are often the thicknesses of sort of tens to hundreds of nanometers. But a property of the gas is called the mean free path of the gas. And this is the average distance that molecules in the gas are traveling before they collide with each other. So I've got molecules of gas flying around, and on average, for air at atmospheric pressure, it's about 70 nanometers on average before each molecule of gas collides. When you do continuum mechanics or classical fluid dynamics, you're always assuming that the length scales of your problem are much, much larger than any of the molecular scales of the fluid. And what that allows you to do is treat the fluid as a continuum. But it turns out that here that this isn't actually true for our problem. The length scales involved, so this film thickness, is actually comparable to the mean free path of the gas. And this is why we aren't getting the correct critical speed with our previous model. This gets described in terms of the Knudsen number, which looks like this, so the ratio of the mean free path to our height. So normally, the sort of normal continuum mechanics to be valid, then we'd need the Knudsen number to be very, very small. But in this case, we start approaching Knudsen numbers around 1. But gas flow between two plates at non-trivial Knudsen numbers is actually a relatively well-studied problem. So for Knudsen numbers that are non-trivial, so I'm sort of saying roughly much bigger than 0, but still much less than 1, then there is this known correction to the mass flow rate. And effectively what that ends up happening is that the velocity profile ends up having this slip length where it's no longer a perfect sort of 0 boundary condition down here, but the velocity is sort of non-zero at each of the walls, roughly with some slip length that is comparable to the mean free path. And it's also been well studied sort of in the context of micromechanical processes. So when you've got very thin leads and sort of mechanical things rather than in droplets, people also know what happens at very large Knudsen numbers. So it's been worked out that the flow rate goes like this Knudsen log Knudsen squared expression at sort of large Knudsen numbers. And what we can roughly see here is that at each of these regimes, we've got some flow rate that has some pre-factor that's a function of the Knudsen number. And so what the previous work by my supervisors and collaborators did was to work out a sort of fitted factor. So this is in front of our volume flow rate here. We've got this delta P factor that's a function of the Knudsen number, which again is the ratio of the mean free path over our thickness. And this factor interpolates between these two extremes. And so what I'm plotting here is on blue is this Knudsen factor, dependent factor that we're including in our model. The red dots are some Boltzmann equation simulations. These are equations of the exact of the dynamics of a gas, including the fact that it's got these individual particles. And then the dashed lines are these asymptotic expressions that I had down below. And so we've got this single factor, delta P, that is capturing this dynamics. So this is all a bit mysterious at the moment that we've got this extra factor. And I've been talking about this being in terms of this Knudsen number. And as a little bit of a side, I thought it'd be worth telling you about where this actually originally comes from in terms of the understanding. So this starts with a series of experiments on flow at sort of reduced pressures in sort of earlier 20th century. So here's the experiments that Knudsen actually worked on, where this originally came from. So our setup is, I've got some pipe that's some length, big length L, and some thickness H, and I've got my flow through it, and this flow is just being driven by some pressure gradient that looks like this. So I've got some pressure at one end P in, I've got some pressure at the other end, and then I've got some gradient in between that looks like this. And I want to think about, here's my midpoint of my tube, and I've got my flow rate. And so I roughly know that my mass flow rate at the midpoint looks like this, where this road here is, this is the density. So this was our volume flow rate. So if I multiply density by the volume, this is my mass flow rate. And what they were measuring is that if we fix our pressure gradient, so I'm going to fix the steepness of how much the pressure is, but I'm going to then vary how the pressure varies in the middle. And I'm doing this by changing the pressures at both ends at the same time, right? But keeping the pressure gradient constant. And the question we want to ask is, well, how does my mass vary as we vary this mid pressure? Now, for an ideal gas, and we're sort of assuming we've got a reasonably well-behaved gas, at constant temperature, the pressure is proportional to the density. So I expect it to look something like this. So if we've kept our pressure gradient constant and everything else keeping the viscosity constant, keeping the thickness constant, if I'm varying midpoint pressure, which means I'm just varying this density at the midpoint, then my flow rate is going to look like this. And I've just normalized the flow rate by the flow rate at P is equal to 1 to B1, just so it's easier to look at. But what was found is that if you go to low enough pressures, this just isn't at all what the actual experiments look like. And then in fact, the flow for the curve ends up looking something like this. Whereas you decrease the absolute pressure, was keeping the pressure gradient constant, you actually find that eventually, so I'm decreasing the pressure going this way, at some point the flow rate actually starts increasing. And this is called the Knudsen minimum, and so this is what started off, or at least was one aspect that started this investigation to this sort of low pressure domain. And again, so these points here are Boltzmann equation simulations. So the fact that that then confirmed what the experiments were suggesting, and that gave us this minimum in our flow rate. And it's this effect that we're capturing in my delta P factor. If I go back to here, so in my equations, I'm including this delta P factor, and it's this Knudsen minimum that we're capturing in our equations. Okay, so again, this is all sort of complicated, but in conclusion, all this means is that I've got this extra delta P factor in my lubrication equation in my model. So, okay, what we've done was very complicated. I've got all this additional physics that I need to include in my model. But what we can do now is, now we've got it, I'm now ready to show you some actual results, and we can see what this model actually predicts. So before I can show you results though, I need to say how I've implemented it. So now that I've got my model, I'm going to solve it in a finite element framework with a moving mesh. So here's a picture of one of my meshes as it evolves, and I'm moving the mesh with the surface. So how this works is you solve for the flow inside the drop, and that gives you the velocity on the boundary, and then you update the velocity of the surface of your mesh based on what you've calculated, and then you move the interior elements of your mesh, assuming sort of treating the mesh like a sort of elastic solid. And that allows you to move the mesh with the solution that you found for the position of the drop. And what this moving mesh method has let us do is resolve very, very thin films, because all we're resolving is the position of the mesh tells us how thick the gas film is. This has been implemented in the open source finite element solver oomph-lib, which was developed by a group at the University of Manchester. And then I've done an overlay. So in red are my simulation results overlaid on some experimental pictures. And so at least macroscopically, we've got great agreement. The experiments and the simulations line up really well. So here's some results. So what I'm going to now show you are what these collisions look like. In the middle, I've got a macroscopic view of the two drops colliding. And then I've blown up by a factor of about 1,000, so you can see the actual shape of the gas film. And then I'm measuring this minimum film thickness in the middle of the drops. And then this is what I'm plotting on the left on a log scale against time. So here are my two drops colliding. And then we can see that the gas film is getting squeezed, but that there is a bubble of gas that is trapped in between. And then the drops bounce apart. Now, what I'm showing in this video is the first simulation where the drops bounce rather than merge. So if the drops are going slightly slower, then here is where you can see that these are slightly slower impacts. I've also plotted these minimum film height curves and they would go to zero where the drops would merge. But instead, this one is then bouncing. And now this is instead the last simulation that I ran before the drops merged again. So this is as fast as I could make it go before they merged. And again, you can see that for the ones that are going slightly faster, the minimum film height would go to zero. And again, there's all of this detail in the dynamics of the gas streams that you can't see at the macroscopic scale. Okay, so here are all those simulations. And I'm again plotting the minimum film height. So here with this direction is where the speed is being increased. So the lowest speed ones are merging, higher speed ones are merging, and then the intermediate ones are all bouncing. And then I've picked this particular liquid parameters because this matches up with what were done by these experiments in the last a few years ago. And we've got great agreement for the critical impact speeds. So we are correctly able to capture how fast we need to make these drops go to make them go from bouncing to merging. So sort of success, we agree with the experiments, which is really nice. So now what I've done is I've now run a whole load of simulations for various different drop radii and impact speeds. And so outside of the red curve is where the drops merge, inside is where the drops bounce. Red curve is where my simulations suggest that we change from bouncing to merging, and the red points are the experiments. And again, great agreement. However, the way these actually tend to get reported, instead of just reporting just the impact velocity, we tend to report the Weber number. So this is a non-dimensional number that captures the ratio of the kinetic energy of the drop to the surface energy, and basically gives you a sense of how violent the impacts are. So higher Weber number, more kinetic energy compared to surface energy, so more violent impact. And if we plot the Weber number, this is what the curves look like. So they tend to tail off to sort of roughly a constant Weber number for these critical impact speeds at larger radius. Now, what I also did was run a set of simulations where I turned off this extra kinetic factor. So just solved the sort of classical lubrication equation for the gas. And this is what the transition curves look like. So completely wrong. You get completely the wrong result. You assume that you need a way higher Weber number to get the drops to merge if you don't include the gas kinetic factor. So this delta P depending on the Knudsen number. Which is what's really nice. This really confirms that this sector factor that we've included in our model is absolutely essential to capture these dynamics correctly. So what we've also looked at are experiments that are done at different pressures, so different gas pressures, and in different gases, so in air and nitrogen, effectively the same thing in this case, or in helium. And again, we can see that we're agreeing decently well. So the solid curves are the simulation boundaries, the points are experiments, and except for one experimental point where we're not quite sure what's going on there, but otherwise we're agreeing really nicely. Now, what I'm plotting here is dependence on absolute gas pressure. Normally, if you're solving classical lubrication equation or even solving full Navier-Stokes equations, the pressure only appears as a derivative. And so changing the absolute value of the ambient gas pressure wouldn't make any difference, couldn't change the result of the simulation. But I've got my mean free path parameter, which appears in my Knudsen number and therefore appears in these extra factors that I'm including. And for constant temperature, the mean free path is inversely proportional to the pressure. So all of the effect of changing the ambient pressure is through changing this mean free path. And so instead, if I just plot this against inverse mean free path, then the data for the different gases collapses onto a single curve, which is really nice. So it turns out that what matters, as long as the gases has roughly the same viscosity of the gas, then all that matters is this mean free path, and the data collapses really nicely. So now what we're looking at are, okay, we found the boundaries between bouncing and merging, but the question we next wanted to ask was, okay, well, how does this merging happen? And what I'm plotting here in the color is what I call normalized contact time. So what I've done is I've run a simulation where with the sort of ability for the drops to merge turned off, so without that van der Waals disjoining pressure, and then I've compared how far through the bouncing process do the drops actually make contact and merge together. And we see roughly the trends that we would expect. So if I increase my impact speed, then the contact time happens earlier, so the drops merge faster. If I increase the pressure, which means decreasing the mean free path, so going this way, then I see that it takes longer for the drops to merge. Sort of gas is harder to displace, and that's what we would expect. And again, below the soft transition, we see that it takes much longer, which is what we observed in the videos I showed earlier. But what's really interesting in this plot is that there's clearly some structure within this merging region, so that this part of the bounce merge boundary seems to sort of continue in some sense into the merging region. And in order to understand what's going on, we can instead look at where does contact occur. So now, instead of plotting the contact time, I'm plotting the contact position. So what I've looked at is at the moment of contact, I've looked at, okay, what's the radial extent of the maximum of the drop? Here's where contact occurs, again, compared to the middle of the drop. And how large is this contact position? And we can see very clearly that there are clear bands of structure within the different contact modes. There are clearly different ways the drops are making contact. So in this region, this is at very low pressure and at high Weber numbers, so highly violent impacts at low pressures. Contact happens very quickly. So where the drops are barely spread, and we see contact happen quite near the axis of the drop. If I increase the pressure a little bit more and go into this region, now we see that contact happens right at the edge of the film. So the drops have spread more, and it's right at this edge at which contact occurs. If I increase even more, we now find that the gas film stays stronger for much longer. So this is at larger ambient pressure. Gas film is stable for much longer. The drops have really spread out now when they make contact. And there's this very elongated flat section of the gas film sort of in this region underneath the drop. And that effectively it's random at what point along the film here contact occurs. And this is why this region that's sort of speckled, because depending on the exact way that the numerics have happened and the remeshing and the slight fluctuations, numerical fluctuations have caused contact to happen at different points along this film. And although everything, my simulations are I don't have any randomness in my actual simulations other than just sort of numerical fluctuations, we think this is probably comparable to what happens in reality, because if I've got a very long spread out film like this, there will also be thermal fluctuations on the surface that are sort of vaguely comparable to these numerical fluctuations. And so we do think that this is perhaps the regime that would actually be seen in reality as well, except instead of numerical fluctuations, it's thermal fluctuations that would cause the sort of start of the unstable waves that would occur along this film. But this is something we're not completely confident on, and would have to look in detail, perhaps including thermal fluctuations, but that's definitely future work. Oh yes, sorry. So here's an example. So here's an example where it happens in the middle of the film, and then very nearby, slightly higher pressure, now contact happens at the edge. And then down below the soft transition, so here's this region where we're getting merging happening for very low speeds. It happens when the drops have not deformed much, but there's quite a large bubble of gas that's trapped underneath the drop. Final thing, we've also looked at water drops. So everything I was doing was for alkane tetradecane drops. But we've had less good agreement for water drops. but we found that if you can change the radius slightly, you get to these quite different curves depending on how the pressure behaves, and that by changing the radius, so these experiments get reported for a range of different drop radii and then averaged. And so what we found is that you can change the radius and sort of go either side of where the experiments suggest. And what this led us to think about is that perhaps this is much more sensitive to the radius than these original experimental papers looked at. But why we aren't capturing the behavior of water drops at much larger pressures, so smaller mean free paths, we're not sure. This is still a sort of question mark of why we weren't agreeing for these larger pressures. Okay, so that I've currently talked about the drop impacts, and I now want to tell you a bit about what I've been doing, what I did more recently, which is on drop bath impacts. So what I'm thinking about here is a sort of similar setup, but instead of a drop, two drops colliding, I'm thinking about a drop impacting a bath. So I'm going to have two Navier-Stokes domains, and I'm going to set up a lubrication equation based on the film height that I'm measuring here. And this is effectively the same equation that I had before, just accounting for the fact that I've got two surfaces that are moving at different velocities. But otherwise, this is the same equation that I was solving before between two drops. But I had a go at this first, and this didn't work. And the reason is that this way of measuring the height isn't correct. So if I sort of start over here, and this roughly is going to give me the correct measure of the height, but if I come further around the surface of the drop, if I'm over here, measuring the height vertically isn't actually going to give me a correct measure of how thick the gas film is. And what I actually need to do is measure the gas film in the normal direction of the drop. And so if you think if I was measuring just vertically over here, that's not the correct sort of amount of how thick the film is in terms of, say, how strong that Van der Waals disjoining pressure interaction is. So what I then had to do is I've then set up, how do I write down the lubrication equation measuring the thickness in the normal direction to the drop on this sort of curved surface. And so in order to do that, I've got to solve a differential equation on a curved surface. And so what we've done is then looked at how this is actually otherwise a well-studied problem, but in different settings. I've got my drop surface parameterized by some coordinate s. I've got my normal, and then I'm measuring my height by projecting this normal. And so what we can do is we can set up a coordinate system within my gas film that's being measuring in, okay, here's my position on the surface, and then I'm projecting out some distance n. That should be an xd, apologies, that's a typo. So that should actually be xd on my surface, and I'm projecting out in the normal direction. And then I can work out what derivatives, what the gradient, what the divergence are as I move around in this surface that's parameterized as the distance away from some curved surface. Okay, and you work through doing how lubrication theory, but in this curved coordinate system, and eventually you get to this differential equation, where now in my lubrication equation I've got these curved derivatives. So this is the divergence with respect to a curved surface, gradient with respect to curved surface, and so on. But this now correctly captures the dynamics of the gas film, but accounting for the fact that it's curved. The thing that's particularly difficult to calculate is this time derivatives dH/dt. So if you think about, here's my height, and there are several different ways that my height can change in time. So it can change because the position of the drop surface moves. It can change because the normal moves. So even if xd in my position here stays constant, if it's sort of my drop surface is rotating around it, then my normal could swing and change the height, or my bath surface could also be moving. And so that's one bit, is then you work out correctly how to calculate this in terms of the time derivative of all of these quantities. But once I've done that, I can then have a correct description of this curved gas film. So here's a video of what the solution looks like. So I've just taken my axisymmetric simulation and just spun it around in 3D so we can look at what one of these drop impacts actually looks like. And I'm just thinking this looks really nice. Nice drop impact, and causing the bath to rebound. And you can really see that this bath is deforming a lot, and that this curved description of the gas equation will be necessary. So here's that same simulation, but just plotting what the actual simulation looks like in the curved coordinate system. So what I'm plotting in the middle thing is the macroscopic view. What I'm plotting below is the height of the gas film. The solid line is what I'm actually solving for, this normal height. The green dashed line was that incorrect vertical height, and you can see at key moments that's actually quite different to this normal height. And then what I'm plotting at the top here is this minimum film thickness. And then these red dashed lines are slightly higher speed simulations where they actually verge rather than bounced. So here's the results of doing a sweep. So inside the red curve is where I see bounces, outside is where I see merges, and again we're changing the drop radius and the Weber number. And then we're comparing to a few experiments that my collaborator Dan Harris did, and we've got great agreement. Like, we were amazed at how good this agreement was for these critical impact speeds. Like, it's fantastic. We were really pleased. But what we were thinking about is, okay, actually, to get down to see this really interesting behavior when the Weber number suddenly drops off, you would want to, well, we'd want to be able to study this, but the difficulty is that these experiments, when you change the impact speed by just physically dropping the drop from a higher distance, and then you let gravity do the work for you of changing your impact speed. And so actually there's a maximum speed of the experiments, which is the terminal velocity of the drop. So the drop can't fall faster than the maximum speed that's allowed because of the drag. And if we assume Stokes drag, which is a sort of simple expression for this drag on a falling sphere, then it's this dashed line is where the sort of inaccessible region, so to the left of this dashed line is the sort of inaccessible region of drop release experiments. And it turns out that this is beyond the region that we want to look at, which on the one hand is disappointing, but on the other hand gives us some ideas of where we might want to do. So what option is you can get faster than the terminal velocity by projecting your drops at speed, which is definitely one possibility that we've looked into. And then the other option, though, is instead of changing experiments to access this region, we could look at slightly different settings. So if we instead change the ambient pressure for gas, change the ambient pressure will decrease this critical impact speed. And I've then run a set of simulations to see what these boundaries would look like at reduced pressures. And they would bring them very nicely into the accessible regions that the experiments could then look at. And so this is what actually Dan and his postdoc Chase have been working on very recently, and I've got some results, some preliminary results I can show you in a second, but we're making excellent progress at sort of using this reduced pressure technique to explore these dynamics with experiments comparing to these simulation results. How am I doing for time? Okay, I'll quickly mention this, but we've also looked at the low speed. So if I zoom in on this lower part of my curve, what's interesting is there's actually this little uptick that happens when you get to large drop radio for the sort of soft transition, where we go from merging to bouncing at low speeds. And we found two very distinct regimes. So one regime where the drops sort of they go from bouncing to making contact to merging, which is what we've seen so far. But there's also another regime where instead the drops go from bouncing to a regime that we've been calling floating, where the drops don't merge immediately, but they don't jump off the surface either, and they float for an extended period of time. So here's what the merging regime looks like, where this is again this is the bouncing case, and if I decrease the speed slightly, then we would see merging just before the drop would release from the surface. And here's what I mean by floating, where instead the drop doesn't manage to have enough energy to jump off the surface, but instead these drops can float for an extended period of time on this captured air film. And again, something that we're now looking at is doing experiments of this regime to see if we can compare. What we've also done is done some benchmarking against other simulation methodologies. So what I've got here is a comparison to a volume of fluid method using the very widely used software Basilisk. So in the red is the volume of fluid simulation, and the blue is my finite element gas lubrication simulation. And excellent agreement macroscopically. We can see that we're absolutely spot on with comparing these two methods, which is really impressive. Although these are both theoretically solving Navier-Stokes equations for the liquid flow, the way these two methods work is completely different. This normally volume of fluid simulations are set up in such a way that when two liquid surfaces get close enough, they would naturally merge. This version is one where you force the drop and the bath to never merge in this volume of fluid comparison. And it turns out, we were very pleased with this, if you do that, then they agree very, very well with my finite element simulations. We also did a case where we let the volume of fluid version Basilisk do what it wants and merge when the fluid gets close enough, and we found complete disagreement. So the different red curves here are a volume of fluid simulation at different levels of refinement, and it merges almost immediately, whereas my simulations suggest that it would take much longer for it to merge. So this is a case where my simulations suggest that the drop and the bath will merge, but they don't merge, I suggest, until the very end of this video. Whereas the volume of fluid simulation, which has generally been thought to accurately capture these sorts of dynamics, just completely disagrees. It sees merging, but the merging happens way, way sooner. Now, we think this is actually a very narrow range of parameter values where we'd see this much disagreement. But this has led to a lot of questions, and we're now thinking about, I think, the fact that how long this gas from my simulation success could stay stable before merging occurs, I think, was surprising. And is something we definitely want to think about and do some more experiments of and think about more in the future. So finally, stock presses. I've only gotten these in the last couple of days, but Chase, who is working with Dan at Brown, has now done many, many more experiments. So the colored points are the experiments. Yellow is where we see bouncing, dark blue is merging, green is floating, and the solid lines are my simulation boundaries. And we've just been amazed at how good this agreement is. So although at this very low radius case, there's slight disagreement, but even so, we've been really pleased at how well this is agreed. And then again, we've repeated it. So this is what I was suggesting earlier, repeating for a lower pressure. So this is at like a quarter of atmospheric pressure. And again, so this is now, you see much more merging, but again, the boundaries that compare my modeling approach to their experiments are again really nice. And we're continuing to work on this. So now we've looked at varying the radius at two different pressures, and we're now working on fixing the radius and varying the pressure and seeing how this affects the outcome as well. But this is ongoing work. So just briefly, there are loads more related problems. So we could think about impacts on very, very thin liquid films. And the question is, okay, does this still impact on a thin film behave like impact on a deforming film, or impacting on basically a smooth solid surface, and that the film being impacted wouldn't merge very much? And when do we go from this case to the other? Thinking about the collision of unequally sized drops. So in raindrops, they're not just two same size drops mostly colliding. It's often one big drop collecting smaller drops. And okay, well, how does this behave? And then also thinking about heated drops. So there's the classic thing about Leidenfrost effect, where a drop, if you have a hot plate with a drop on top of it, a drop can levitate on a sort of layer of its own evaporating gas. And again, using this simulation methodology to try and simulate this. Let's see if I get this to play. There we are. This is another 3D video of my drop-drop collision we saw earlier. So I was part of a CDT at Warwick called Modeling of Heterogeneous Systems, or HEXIS, that I was part of, who were a big help whilst I was doing this research, as well as Warwick's SCRTB Community System and Institute for Advanced Study that I spent some time at in my last year at Warwick. And without them, this work couldn't have been completed. We've published the work on drop-drop collisions, which I would if you're interested, please go ahead and read. And we publish the code for the drop simulations as well. And papers writing up the drop bath work are currently in progress and should be published sometime reasonably soon. So thank you very much, and I'm happy to take questions. I've realised this has gone on a bit longer than I think, but I think we had a delay with tech at the start, so I'm hoping I've not actually overrun too much.
Thanks, Peter. No, don't worry about it at all. It's spot on timing, I think. So
okay.
So yeah, thanks a lot. That was a really interesting talk. We've got time for questions. I mean, people, you're welcome to obviously to drop off as of when you want if you've got other activities.
Yeah, I realise we've pushed ahead on time, so I'm also happy to take if people have got questions if people want to email me, I'm happy to take email questions as well. But I can hang around for a bit now as well if people have got questions. Either way,
open up the floor to the audience. I mean, I can start. I have one question.
Yeah.
On slide 13, you showed this like comparison between the critical.
Yeah, let's go back.
I can't remember exactly. It was like maybe it was the merging.
13 was
U-crit is what I was looking at.
Oh yes, this all I mean is the critical speed. So below this they bounce and above it they merge.
And how did you calculate that in the model? Is there some like?
So all I'm doing is I'm running the model at different velocities.
Right.
And yeah, let's go back. All I'm doing is running the velocity at different models and just observing what happens. And then I write down so I think these are probably like I was doing 0.5 spacing or something, and I say this is the value that it goes from. So where let's go to one of the phase diagrams. Yeah, here's a good example. So here I'm like going from, I've done 4 simulations here at different speeds, so like 0.42, 0.42, 0.44. And so all I'm saying is, so these ones bounce and these 2 ones merge, and I'll just report the critical speed will be a value in between them. And so then there's an error bar around it as well. And in the paper, we report the size of these errors as well. But for the presentation, I didn't include that.
Were the errors like reasonably large? I mean, they look quite small there. So
yeah, I mean, the simulations are perfect. There's no randomness, so I can just run simulations at any impact speeds I like, and I can make that value as narrow as I want to. There is uncertainty in the experiments we compare to, so there's not much point for refining my exact critical speeds like way beyond what the resolution of the experiment is.
Yeah, that makes sense. So, audience, anyone, you'll pop your hand up.
I had a question about this. So you your drops as they approaching each other, they start off as circular.
Yes.
Yeah. Is that actually the shape at the terminal velocity of a droplet as it falls? Because
that is a really good question. Everything we've looked at has been assuming that, and for small drops that is true. You need the surface tension, or I guess think of it in terms of the capillary number, when surface tension to be sort of dominant in its sort of static case for that to be true. And effectively for the size of drops we're looking at, we think this is correct. But you don't need to go that much larger than the drops we've looked at, so sort of beyond millimeter size for these oil drops, or for water drops are roughly the same as well. At which point we think the shapes they'd be falling at these terminal speeds wouldn't be spherical anymore. And that very well might change whether the drops bounce or merge. It's something I would definitely suggest should be looked at in the future. The problem is there isn't a sensible choice to choose as the initial condition that isn't spherical. Because if the drops are falling and we sort of don't know what their impacting is, well, what do you pick instead of a sphere?
Well, you could assume it like just a infinitely flying in a torus droplet.
Yeah.
And then what's its equilibrium size for a given speed?
Yes. No, you are right. You could work out what the equilibrium shape with the drag on them is. No, that's absolutely true. Yeah, that's a good thing to be looked at in the future, actually. I know we looked at estimates for how non-spherical they would be, and in the cases we've looked at, they're all pretty spherical, but for a different regime, you could definitely do that. And that's definitely a good suggestion.
Is the thing that got me like that, where I was sort of confused, was also on that slide 11 where you show that dip, that it's like almost trapped air in there. That how, you know, where you show that two drops sort of almost have that ring of touching. That is that, you know, is that now the air that is trapped in there, inviscid or incompressible Navier-Stokes? Is that?
Yes.
No.
So we are assuming incompressibility, and we've checked that the excess pressures that we get in the simulations are still moderate, that incompressibility is a reasonable assumption.
But why is there that ring? Why are you assuming that ring?
No, there's no assumption of the, as in the fact that it sort of dimples down.
Yeah.
Yeah, no assumption. That comes out, you run the simulations and that's what it looks like. And effectively, what's causing that is surface tension. So it's without surface tension, it's sort of flat and then would be round. And surface tension just sort of rounds off the edge of this gas film. But there's nothing imposing that. I've just drawn it as a sketch here because that's what it looks like in the simulation results. And in fact, yeah, you can see it here that this is basically what it looks like, is that there's a trapped gas bubble and then it gets much closer right at the edge of the gas film. But we're not imposing that. That's just what the simulations find. And
that's experimentally shown.
Yes, it has also been experimentally shown. So not for the cases I've looked at here, but a similar problem is the impact of a drop on a very smooth solid. So if you have an atomically smooth solid and you impact a drop on it, and again, the gas there, you can trap the gas and the drop is able to bounce. And people have done various microscopy techniques to measure the thickness of the gas film, and it looks like this. Yeah, this is genuinely what the shape of the bottom of the drops look like. But we can't see in experiments inside two colliding drops, which is part of why these sorts of simulation methods are so valuable, in that for these cases, you can't use microscopy techniques.
Why can't they see it? I'm just
I mean, if I've got two drops, how am I going to see the gas film that's trapped in between them?
With some sort of laser system.
I'm not an experimentalist. All I know is I've seen no experimental measurements of the gas films within colliding drops. People have done it for drops on smooth solids where you can look underneath like a transparent smooth solid and see it, or drops on people have measured it for drop on back impact. But for drop collisions, I mean, these films are really thin. Like we're talking like tens to hundreds of nanometers. So they're much smaller than even these drops, and these drops are flying pretty fast. Like these experiments look like you've got drops bouncing like this. But I'm not an experimental expert. It'd be great if someone was able to do the experiments on these and actually measure these films. That'd be fantastic. But I've not seen it.
Okay, thank you.
No, thanks. Oh, really good questions. Yeah. Thanks.
So no one's rushing to say anything else. So on that, let's thank Peter again. So thanks very much, Peter, for your talk. And so do you want to say a little bit about like what you're doing now at your postdoc?
Yeah, I can do. I'm doing something very different. So I'm looking at hydrogels. So these are gels where you've got some sort of polymer network and then it's filled with liquid till they're like 95 up to 99% water, but they still behave roughly like soft solids. And in particular, I want to look at ones where you've got electrolyte solutions. So these are called polyelectrolyte gels, where you've got salt ions inside the liquid that's inside the gel. And what's been found is that these will respond to external electric fields or external applied electric currents and deform. And they're very useful in sort of soft robotics applications. But what hasn't been done yet is incorporating how the electrical interactions of the ions between the polymer network and the ions inside the liquid interact. And we want to do sort of mathematical homogenization to incorporate the electrical effects at the small scale to get to some equations that describe these polyelectrolyte gels at the big scale. So it's a very broad picture overview of what I'm working on, but I've only been here for a couple of months, so this is sort of early stages. But yeah, so sort of more soft elastic solids than fluid dynamics. But in some sense, it's sort of very, very big picture related in that I'm looking at small scale physics, how that affects the macroscopic behavior of some dynamical continuum mechanics system.
Sounds good. Congrats on the position. So I'll stop the recording there. So if you're on YouTube, hope you've enjoyed, and leave a comment, send Peter an email, and like and subscribe and whatnot, and see you at the next one.